Welcome back. Today we're going to be talking about homeostasis. This is a really important topic in A&P and one that we will be coming back to again and again. If you break down the word homeostasis, homeo means same and stasis means stable. So homeostasis is the tendency of the body to kind of stay the same, stay stable. Meaning that we don't want wild swings in blood pressure and wild swings in glucose levels and wild swings in other things in the body. We want our bodies to mostly stay stable. And we want this to happen even though we're going and doing all kinds of strange things. We're going outside in the heat or the cold. We're running up and down stairs. We're eating, massive amounts of candy. We want our bodies to be able to deal with these changes and bring the body back to normal. So this doesn't mean the body never gets out of whack. It means that we bring it back to normal very quickly. An inability to do this results in pathology. So the first thing we have to talk about is the stimulus. So the stimulus is when there is a change in a set point outside of normal. So what's a set point? A set point would be something like your body temperature. We all know that body temperature is generally around 98.6 degrees Fahrenheit. And that's sort of the set point. It can go a little bit up, it can go a little bit down, but usually your body temperature really just doesn't change that much. When it gets really high, like 104, 105, that usually signals that there's a significant problem going on. You have some kind of infection. If it gets very low, that also is a significant problem. You're hypothermic and you are at risk of all kinds of other problems. And so the set point for body temperature is right around 98.6. If you get too high or too low outside of the normal, that's a stimulus. It's important to recognize that the stimulus has to be something that your body can recognize and measure. So for example, maybe you fell in a freezing cold lake and you've been in the lake for like 15 minutes and your body temperature starts to go down quite a bit. It's not that you're in the lake that the body measures. It doesn't know that you're in a lake. All it knows is that the body temperature starts to decrease. So the stimulus is the change in a normal set point. We have a lot of different set points. So for example, blood pressure, right? Blood pressure is normally somewhere around 120 over 80. If it gets too high, that's outside of normal. And if it gets too low, that's also outside of normal. And so when that happens, when you have a stimulus of the blood pressure, say getting really, really low, the body is going to react because it's a stimulus and it's going to trigger this next component in the loop, which is called a receptor. Now, there are other stimuli. For example, your heart rate, right? Your heart rate is usually around 70 beats per minute, but I think normal is like anywhere between 60 and 100 beats per minute. And you can see that all of these things are things that can be measured. Heart rate is measured. It's not, I did a bunch of exercise and so my body is going to try and fix it. It's my heart rate went way up above normal. So the stimulus, again, is not what you're doing. It's a change that can be measured. pH also can be measured at around 7.4. And all of these can be measured by different types of receptors. So we will talk lots more about receptors in the nervous system, but just so you know, temperature is going to be detected by a special kind of receptor called the thermoreceptor. Pressure is going to be detected by something called a baroreceptor or pressure receptor. And pH will be detected by something called a chemoreceptor that's going to detect the amount of chemicals in your blood. So all of these are detected by receptors. Receptors detect the fact that there's a change, and it's going to tell something, another part of the body, that there's been a change. That part that it tells is called the control center, and it's called the control center because it has a very important job. The job of the control center is to receive information from the receptor that something is not right. We're out of normal. Say, for example, your temperature is really high. That's not normal. Your control center is going to receive that information. It's going to make a decision, and it's going to send instructions out on how to deal with that situation. When it sends the information out or the instructions out, it's sending it to the effectors. There's 3 different types of muscles that can work as effectors in the body. We'll be learning much more about muscles in the coming chapters, but for now, these are the 3. So skeletal muscles are your voluntary muscles, like, when you move your arm, your leg, whatever. Those are your skeletal muscle. Smooth muscle are involuntary. Oops, I'm about to write involuntary. Smooth muscle are involuntary muscles. And so those are the muscles that line your organs, and they're inside your blood vessels, and they are involuntary. We also have cardiac muscle. So these are the 3 types of muscles that can be effectors. We also have one more type of effector, which are glands. So when the control center receives information from the receptor that there's something wrong, it has a couple of different areas that it can instruct to do something about. Now, those effectors have 2 things they can do. The first thing is they can do something that will get rid of this stimulus. When that happens, it's called negative feedback. And reason it's called negative feedback is because we're negating the stimulus. So for example, say that you get really cold and your body temperature falls. So if it goes low enough, it's going to trigger a receptor. The receptor is going to tell the control center. In the case of body temperature, the control center is in the brain. It's called the hypothalamus. We will also learn about that later. And the control center is going to tell the effectors to do something. It's going to give them some instructions. In the case of being too cold, one of the things that it's going to do is it's going to target these skeletal muscles, and it's going to tell the skeletal muscles to start contracting very rapidly. And when those skeletal muscles contract very rapidly, they use a lot of ATP. And as we're learning about, when we use ATP, we need to make more. And when we make a lot of ATP, there is a lot of energy that is lost as heat. So we're making ATP so the skeletal muscles can contract rapidly. We also call that shivering. But as a side effect, we get a lot of heat produced. So remember, we were too cold. Once the skeletal muscles start contracting, we're going to bring our body temperature back up. That'll get rid of this stimulus. So that's one way we can get rid of the stimulus. There's another type of feedback that's called positive feedback. So what positive feedback actually does, so remember this one gets rid of the stimulus. Positive feedback increases the stimulus. If you can see what I'm writing. Yeah, I think so. And what's interesting about that is that the majority of homeostatic loops in the body work by negative feedback. Most of the time, we're trying to get rid of the stimulus. Occasionally, we're trying to increase the stimulus. But there's only a couple of examples of positive feedback that we're going to talk about in this class. And I'll talk about that in just a minute. So we've already talked about temperature and our body temperature being too low. One way we can bring our body temperature back up is by causing shivering, and that's going to cause all this release of extra heat and raise the body temperature. The other thing that the control center is probably going to do is going to target the smooth muscle in your blood vessels. So when you're very cold, we want to retain heat in the core of our bodies. That's where all the heat is. That's where all the really vital organs are, right? Your heart and your intestines and your brain and all of that stuff. And so we're going to reduce the amount of blood that goes to the extremities, to your hands and to your feet. because that's where we lose a lot of heat from. And so the control center is going to cause these skeletal muscles to start contracting, but it's also going to cause the smooth muscles in the vessels that go out to the periphery to contract. So when you have a vessel that contracts, it makes that blood vessel smaller. Less blood goes to the periphery. This is why frostbite is so dangerous. As you get colder and colder, your vessels constrict, less and less blood gets to the extremities, and those fingers and toes and maybe your nose don't receive enough blood to keep the tissue alive. So those cells start to die. And that's when you get those white patches. Sometimes they even turn black if it's bad enough. So that would be when the temperature was too low. So temperature low, you're going to have a receptor that tells the control center what's going on. Ooh, we're cold. The control center is going to cause increase in skeletal muscle contraction and also an increase in blood vessel, I think it's EL, contraction, which is something we call vasoconstriction. Vasoconstriction is actually one word. Looks like two, but it's one word. So vasoconstriction. So this is when temperature goes too low. Now, what if the opposite happens? Body temperature goes up. You're hot, right? Maybe you walked outside. It's summer. You're sweating. Well, you're not sweating yet. First, your body temperature will go up. The receptor will pick up that change outside of normal, will tell the control center, oh, got a problem. The control center has a different situation now. Now the temperature is actually too hot. We don't want to do these same things because these were things that we did when our body temperature was too low. So we actually have a different decision that has to be made. Now the control center is actually going to do something different. It's going to target the glands, and specifically sweat glands. So the reason you start sweating when you're hot is because there's a stimulus. Your body temperature started to get too high. Your control center told your sweat glands to produce sweat. And when sweat is produced on the skin and it evaporates, it actually cools your body. The other thing that we're going to do is we're going to cause vessel dilation. When we dilate the vessels that are going to the hands, you can actually see, okay, my hands look terrible right now, but look, I'm really hot. You can tell because you can see all the blood vessels near the surface of the skin. They're all kind of popping out. That doesn't happen all the time. That only happens when it is particularly hot and your husband has turned the thermostat up to 78. And for whatever reason, I'm still wearing a sweatshirt. I don't know. So you can see that I'm actually a little bit hot and my body has reacted by the control center telling my smooth muscles in the vessels to dilate, to bring more blood to the surface and more blood to the extremities to help try and dissipate all of that heat. Okay, so let's move to the next page. So now I want to talk a little bit about positive feedback. So we still have the same components. We have the stimulus, we have a receptor, we have a control center, and we have the effector. Now in positive feedback, we're not going to try and get rid of the stimulus. The stimulus happens, and we're going to do something to actually increase that stimulus. So, for example, the sort of classic example of positive feedback would be childbirth. So as the baby gets bigger and bigger and bigger, it presses down on the cervix harder and harder and harder. And at some point, that pressure starts to exceed normal. Remember, I told you we have different types of receptors, and some of them are pressure receptors. So they identify like blood pressure and other kinds of pressures. One of them is pressure on the cervix. So as that pressure on the cervix gets bigger, the lady who's now in labor her receptors are going to pick up that massive, massive pressure on her cervix, and they're going to tell it to the control center. In this case, the control center is actually the same place as with temperature control. It is the hypothalamus, which controls the posterior pituitary. So the posterior pituitary is going to receive the information that there's a lot of pressure on the cervix, and it's going to tell an effector to do something. And remember, we have different things that can be effectors. We have 3 different kinds of muscles, and we have glands. So in this case, the control center is going to activate 2 different effectors. First, we're going to activate a gland, which is the posterior pituitary, and it's going to produce a hormone called oxytocin. Now, oxytocin is going to be released into the body, and it's actually going to have the effect of causing smooth muscle contraction of the uterus. So now you've got the weight of the baby sitting on the cervix, and you've got this contraction of the uterus pushing the baby down into the cervix. So has the stimulus gone away? No, we've actually increased that stimulus. There's now more pressure. So we have increased the pressure on the on the cervix. The receptor is going to pick up that increased pressure, and it's going to tell the control center. The control center is going to tell the posterior pituitary to produce more oxytocin, which is going to cause the smooth muscles in the uterus to increase the pressure on the cervix, which is going to keep on going around and around. You don't see the stimulus going away in this case. You see the stimulus getting bigger and bigger and bigger. Eventually, that uterus is going to press so hard and with such powerful contractions, the little baby will eventually come out. So there's the baby being born. At that point, there's no more pressure on the cervix. And so eventually this does stop, but the immediate feedback is not negative. It's positive feedback. The immediate feedback is to keep going, to increase what's happening. So there's a couple of examples. One is childbirth. The other one is blood clotting. And the last sort of famous one is orgasm. And you'll have to wait for the reproductive system to talk about orgasms. But for now, just know that all 3 of these are examples of positive feedback in which we go further. The stimulus gets greater. So whatever our response is greater. So what I want you to remember from this is that the control center can be in various different parts of the body. It's not always the brain. Sometimes it is. Sometimes, so for example, in glucose homeostasis, the control center is the pancreas. In calcium homeostasis, the control center is the thyroid gland and parathyroid glands. It's not always the brain. Thanks for watching. See you in class.